Hello everyone and welcome back to my channel. In this video, we'll be continuing our lesson on linear programming. If you haven't subscribed to my channel, please do subscribe. It's totally free of charge. Okay, in previous lessons, we have talked about how to use linear programming to model network flow problems. And just in the last lesson, we talked about how to solve linear programming problems graphically. We also do have LP solvers, online LP solvers that we could use to solve linear programming problems. But it was very important to also show how we could solve linear programming problems using graphs. In today's lesson, we'll be looking at how to use linear programming to model 01 Knapsack. Just a little bit of what we have talked about before. It's important to note that in linear programming problems, we have the variable xi can be real, and when it is real, it can be real. And this is an LP problem, right? And usually its complexity will be O to the nm raised to power c. Also, when xi is an integer, it can be an integer, and when it's an integer, we have an integer LP, right? And an integer LP is always a very hard problem to solve, and that's because this means that all of our answers are going to be integers. And how do we have the guarantee that our actually correct answers are integers? So this is what makes an integer LP a really hard problem to solve. Now, the variable xi can also take 0, 1 values. So, and when it takes 0, 1 values, it can take 0, 1 values, right? And when it takes 0, 1 values, it's solving 0, 1 integer. It's a 0, 1. It's a 0, 1 IP problem. Okay, which is also a very hard problem to solve. So down to today's lesson, we are going to look at how to use linear programming to model 01 Knapsack without repetition. So let's try that. If you remember our lessons from knapsack problems, which we did a couple of many weeks ago, we talked about a knapsack, which is like a bag, and our aim is to have the most value in that bag. But then we have a constraint, which is the weight of that bag. So when we're using LP to model 01 knapsack problem, we have, for 01 knapsack, we're going to have n items. We have n items, then we have our weights. These weights, we could call them Wi that way, or W1, W2, all the way to Wn for the n items. And then we are going to have our values. We have our values, and this would be V1, V2, all the way to Vn. And our knapsack capacity, as usual, would be represented with C. So now let's define what this would be. So every item would be represented with, every item would be represented with X subscript I, and when we choose this item, we are going to represent it with 1, right? 1 if it's chosen, 0 if it's not. And our value in this case would be, this would be our value. We have V1 X1 plus V2 X2 plus all the way to Vn Xn. And our weights would be W1 X1 plus W2 X2 all the way to Wn Xn. And there is something I really need you to notice here. Since our items would be 1 or 0, if 1 if it's chosen, 0 if it's not. So this means that the value of every item that's not chosen is 0. and the weight of every item that's not chosen is 0. So this means that this formula representing the value and of course the weight is only for the items that are chosen. It's only going to count for the items that are chosen, because v times, if we do not choose x2, 0 is 0. So it cancels out everything in this term. I hope that makes sense. So usually for 0, 1 knapsack, our objective function is going to be to maximize. We want to maximize our values, right? So we want to maximize v1 x1 plus v2 x2 all the way to vn xn. And our constraint, we are defining the LP right now, and our constraint is C. So we want, so our constraint is subject to xi being element of this. So we have either 0 or 1. That's the constraint, and our weight and that constraint is always going to be less than or equals C, which is w1x1 plus w2x2 all the way to wnxn. It has a limit, so that's a constraint too. But the thing is, we cannot, I have to emphasize that, we cannot solve 0, 1 knapsack problems using LP, linear programming. For 0, 1 knapsack problem, an alternative is to use dynamic programming, which would not be computationally that expensive to solve. We are going to stop here. In our next video, we are going to look at how to use linear programming to model fractional knapsack problems. And I'll see you in the next one.